Question 6. Consider a pendulum in motion. Which of the following does the pendulum experience? Well, let's just draw a pendulum to start with. We have a pivot point, and we have a little mass on the end, which is swinging back and forth. So, does the pendulum experience force but not torque, torque but not force, neither force nor torque, or both force and torque? Well, let's go through these. Does it experience force but not torque? Well, the problem with this is that it's rotating on its axis, right? It's moving left and right and sort of rotating as it does so. So it has to be experiencing some sort of torque. Is part B then? It experiences torque but no force. Well, that's problematic as well, because remember, the pendulum experiences a gravitational force. And without the gravitational force, there's no torque that will cause it to swing back and forth, right? So it can't be B. So it must experience both force and torque, because you can't have rotation without a torque, and you can't have a torque without a force. So in the case of a pendulum, the force that causes the torque is the gravitational force acting on the pendulum. Question 7. What are the units of torque? Remember, they're not newtons. Newtons are for force, which causes movement. We're looking at torque, which causes rotation. So to find torque, we take the force and we multiply it by the distance between the force and the pivot point. So if we're multiplying a force by a distance, we get an answer in, that's right, Newton meters. So the torque on an object is the product of a force and a distance. Question 8. A spanner has 100 newtons of force exerted on it by a frustrated worker. What is the torque exerted by the spanner if the force is applied 20 centimeters from its axis of rotation? So if we were to draw a diagram, it might look something like this. We have a bolt, a spanner, 100 newtons of force, which is enough to lift about 10 kilograms, give or take. And we have 20 centimeters of spanner, or 0.20 meters, right? So how do we calculate torque again? Well, it's a pretty simple formula. Tau, that is torque, equals d times F. In this case, d is 0.20 meters, and F is 100 newtons, right? So multiply them together. We have 0.020, or 0.20 rather, times 100 newtons, which gives us 20 Newton meters. Question 9. Two children sit on a seesaw. Alice sits 2 meters from the center and weighs 360 newtons. Bob sits 1.7 meters from the center and weighs 400 newtons. Which direction does the seesaw go? Now, if you're younger and you ever played on seesaws, you'll know that if you sit further from the middle of the seesaw, then you'll have a bigger effect on the seesaw than if you sit very close to the middle. And in fact, if you have two kids of different weights, you can still get the seesaw to balance by sitting different distances from the middle, right? So that's what this question is asking about here. What we should look at is the torque produced by each child, and then figure out which torque is greater, and that will tell us which direction the seesaw goes. So let's start with Alice, alphabetical order, why not? So Alice's torque is d times F, d being the 2.0, and F being 360 newtons. So that'll end up as 2.0 times 360, which gives us a torque of 720 Newton meters. So this will be the torque of the seesaw in Alice's direction. Alright, what about Bob? Once again, we use tau equals distance times force. Substituting in 1.7 and 400 newtons, we end up with this expression, which evaluates to 680 Newton meters. So that's the torque in Bob's direction. So which torque is greater? Well, we can see that even though Bob produces a larger force on the seesaw, Alice produces a larger torque. And what this means is that most of Alice's torque is cancelled out by Bob's torque, but the net torque on the seesaw is still in Alice's direction. So Alice is the one that is on the end of the seesaw that tilts down. Question 10. A certain bolt requires a torque of 18 Newton meters before it will come loose, but you don't want to exert more than 50 newtons. So how long does the spanner turning the bolt have to be? Remember, if we have a longer handle, we can produce a greater torque. So, how would we figure this one out? The thing is, we have a measure of torque already, so that's not what we're trying to calculate. We also have a measure of force. What we want is a distance, the distance of the force from the pivot point. So, rearranging the equation, we see that the magnitude of the distance to the pivot point is going to be the torque divided by the force, right? And we'll have to push right at the end of the spanner. If it were longer than this, then we could still push the same distance from the pivot point, but in that case we would be using less than 50 newtons. So our answer here is going to be a minimum value for the length of the spanner. If it's longer, then we can still turn the bolt without exerting more than 50 newtons. So, substituting in 50 newtons and 18 newton meters, we end up with 18 newton meters over 15 newtons, which is the same as 0.36 meters. Of course, this is a little clunky if we're going to be talking about a spanner that is 0.36 meters long, so we might turn that into centimeters. The spanner has to be at least 36 centimeters long. If it's even longer than that, then the bolt will be even easier to turn, right? But 36 centimeters is quite long already, so perhaps that would be a good size. Alright, so that's the end of the questions. In this section we've looked at torque, that is the turning moment of a force, and we've seen how to calculate it. Later this will become very useful when we talk about the torque produced by an electric motor.